Yes, sir.
Okay. So the next question was next question kota chilo Thevenins. Okay. So Thevenins said the problems that regarding the problems where we have to use Thevenins are essentially those types of problems. For example, we have a NPN BJT. So let's say like this. Okay. And in the base terminal, there is a branching. So something like that. Okay. So let's say it's R1, R2. Let's say VCC here, also VCC here, RC, RE. Okay. So now clearly in the base terminal there are two resistors and they are kind of connected parallel to each other. So there is a branching. So in this case, when you have branching, and this is the reason we have Thevenins. Thevenin's theorem is to simplify complicated things. For example, when you have a complicated system, so inside a system you have many resistance parallel to this, or this a DC voltage source, let's say current. Then there's only two terminals coming out from inside and outside. So the Thevenin's theory says that doesn't matter how complicated the whole system is, we can things we can replace the whole thing with a DC voltage source, with a DC volt sorry it's a DC voltage source and a resistor in series. That's it. So everything can be lumped into a DC voltage source and a resistor in series. Okay, where the DC voltage is the open circuit voltage. So let's say this is our VOC, and the resistance RTH is the resistance that you're going to see looking back inside the system. And while trying to determine the resistance, what we usually do, we short circuit the DC voltage source and we open circuit DC current source. There is nothing new that you have already learned. So similarly, you can say have a here there is a complicated thing, something you don't something you cannot deal with on its own. You find it complicated. So if there is a complicated thing, you can say, yeah, I'm going to convert it to Thevenin's equivalent circuit. So that's the part I'm going to convert it to Thevenin's equivalent. Okay. And what is the rule when you want to replace anything using Thevenin's? First of all, we disconnect it from here. So likewise, we disconnect it from here, and then we determine VOC after the VOC, which is in fact is our VTH, and then we also determine RTH. Okay, so if I do that, so first thing we're going to do is to disconnect it from here. Okay, so let's say this is a prime, the disconnected point a prime. Okay, this is R1, this is R2, and this is VCC. So I want to determine the Thevenin's equivalent circuit for this part, and for that we need to determine two things: open circuit voltage VOC, which is is our VTH. And then we need to determine RTH. So the resistance looking back. So open circuit voltage is what? The voltage across R2. So VR2 is our VTH. Okay. So how can we determine VR2? We can determine VR2 number of ways. We can determine the current since it's a series circuit. Remember, it's a series circuit. You know, there's this terminal is open, so no current is flowing there. So it's essentially a series circuit. So if it's series circuit, you can determine the current and then you multiply the current with that voltage, or we can apply voltage divider rule. So what is our voltage divider rule? So VR2 is in fact R2 divided by R1 plus R2 times VCC. That is our VTH. And then if you want to determine RTH, what I'm going to do, I'm going to, if I look back, what are the resistance that we see, equivalent resistance in DC. For that case, what we do, make it, if there's any DC voltage source, we short it out. Okay. So now if you look back, so what do you in fact see? You see R1 and R2 are what? Connected parallel to each other. As RTH equals to R1 parallel R2. ঠিক আছে? So that is how we can determine. Now that we have obtained that Thevenin's equation, so I will replace it. So let's replace it. So replace the circuit with Thevenin's equivalent circuits. This is our RTH and VTH, and A not prime terminal. The rest of the circuit will be connected. So now we have simplified the circuit, haven't we?
Yes, sir.
Now we have come to the circuit where there are resistance in all three terminals, and we know how to solve circuit there are resistance in all three terminals. Now the thing is that you can do it for every other circuit. Let's say there is a resistance here, there is a branching at collector terminal as well. It is connected to the ground, so if there is a branching in the collector terminal, so you can apply Thevenin's here as well. So in that case you can apply Thevenin's. So you disconnect from here. So for example, let's say we R prime. So we disconnect it from here. So first of all, we have VCC. Okay. And then VCC, another one terminal is connected to RC. And RC থেকে কোথায় connect করলো? R prime is connected to the ground. Okay. And this terminal we're going to open it. So RC এবং R prime other terminal open it. Okay. Same as before. So this is our VCC, and if I replace it, we can replace it with a DC voltage source and a resistor in series. VTH prime RTH prime. So that means, so এখান থেকে আমরা কি কানেক্ট করব? আমি যদি আবার ইরেজার ইউজ করি, তার মানে হচ্ছে again, so we replace that part with the DC voltage and the resistor in series. So this is our DC voltage source VTH and the resistor in series RTH prime, VTH prime, and you see rest of the circuit will be connected as it. So এখান থেকে কি কানেক্ট ছিল? এখান থেকে আগে কানেক্টেড ছিল কালেক্টর টার্মিনাল. So similarly our collector terminal will be connected here. From there collector will be connected. You see, doesn't matter where you have branching, even if you have branching here. So let's say you have branching here.
Same with this, sir.
Same with it. Let's say BEE prime. যেখানেই ব্রাঞ্চিং থাকবে আমি সেখান থেকেই আমি ডিসকানেক্ট করে I will replace the whole things with a DC voltage source and a resistor in series.
Yes, sir.
Is that all right?